Hi, and today we're going to be thinking about architecture before we're coding. First, let us talk a little bit, why do we need to architect software? And what exactly is software architecture? To this end, partitioning, knowledge, and abstraction are the three pivotal categories in software engineering when it comes to architecture. Developers partition a problem so that its parts are smaller and more tractable, they apply knowledge of similar problems, and they use abstractions to help them reason. So partitioning, knowledge, and abstraction are effective because they enable our fixed-size minds to comprehend an ever-growing problem. Partitioning is effective as a strategy to combat complexity and scale when two conditions are true. First, the divided parts must be sufficiently small that a person can now solve them. Second, it must be possible to reason about how the parts assemble into a whole. Parts that are encapsulated, we'll get to encapsulation later on, are easier to reason about because you need to track fewer details when composing the parts into a solution. You can forget, at least temporarily, about the details inside the other parts. This allows the developer to more easily reason about how the parts will interact with each other. For instance, if your goal is to design Google Maps, you may choose to separately or independently design the map, the search box, and the information box and hope to be able to assemble everything into the coherently designed UI as soon as the brand book allows you to. Software developers use knowledge of prior problems to help them solve current ones. This knowledge can be implicit know-how or explicitly written down. It can be specific, as in which components work well with others, or general. It comes in many forms, including books, lectures, pattern descriptions, source code, or design documents. Abstraction can effectively combat complexity and scale because it shrinks problems, and smaller problems are easier to reason about. So software architecture is one such weapon that will help you address the complexity and scale of software systems. It helps you partition software, it provides knowledge that helps you design better software, and it provides abstractions that help you reason about software. I'm going to give a few examples from George Fairbank's excellent book Just Enough Software Architecture. They all relate to Rackspace, that is a real company that manages hosted email servers. Customers call for help when they experience problems. To help a customer, Rackspace must search the log files that record what has happened during the customer's email processing. Because the volume of emails they handle kept increasing, Rackspace built 3 generations of systems to handle the customer queries. The first version of the program was simple. There were dozens of email servers generating log files. Rackspace wrote a script that would use SSH to connect to each machine and execute a grep query on the mail log file, so engineers could control the search results by adjusting the grep query. This version initially worked well, but over time the number of searches increased and the overhead of running those searches on the email servers became noticeable. Also, it required an engineer, rather than a support tech, to perform the search. The second version addressed the drawbacks of the first one. The company was now handling hundreds of email servers, so the volume of log data had increased correspondingly. Each email server would send its recent log data to a central machine, where it was loaded into a relational database. Support techs had access to the database via a web-based interface. The challenge became how to get the log data into the database as quickly and efficiently as possible. They optimized insertion into aggregate tables and only kept 3 days worth of logs, so the database size would not hinder performance. But over time, the system also encountered problems. The database server was a single machine, and because of the constant loading of data and the query volume, it was pushed to its limits with heavy CPU and disk usage. Over time, more problems such as failures have started to occur in that server. The third version addressed the drawbacks of the second by saving the log data into a distributed file system and by parallelizing the indexing of log data. Instead of running on a single powerful machine, it used 10 commodity machines. Log data from the email service streamed into the Hadoop distributed file system, which kept 3 copies of everything in different disks. The company has reported processing 6 months of indexed logs spanning across 30 disk drives, and indexing was performed using Hadoop's implementation of MapReduce to build a complete index. Jobs ran every 10 minutes and took about 5 minutes to complete. The first thing to notice from looking at these 3 systems is that they all have roughly the same functionality, querying email logs to diagnose problems. Yet, they have different architectures. Their architecture was a separate choice from their functionality. Despite having the same functionality, the 3 systems differ in their modifiability, scalability, and latency. For example, in the first and second versions, ad hoc queries could be created in a matter of seconds, either by changing the grep expression used for the search or by changing the SQL query. The third system requires a new program to be written and scheduled before query can be obtained. So all 3 support creating new queries, but they differ in how easy it is to do so, or modifiability. Notice also that there is no free lunch. Promoting one quality inhibited another. The third system was much more scalable than the other 2, but its scalability came at the price of reduced ability to make ad hoc queries and a longer wait before results were available. The data in the first system was queryable online, and in the second could perhaps be made nearly so, but the third system had to collect data, then run a batch process to index the results, which means that query results were a bit stale. What is software architecture? So there exists a number of definitions from various sources on what software architecture actually is. And for example, Shaw and Garland define it one way, Clements define it the other way, and the IEEE 1471 define it the third way. What's common between those definitions is that they all share certain parts: components, relations between those components, and properties of both. So I encourage you to stop the video and take a minute to read and understand, or at least try to think about those definitions. You will notice that they are pretty much similar. One question arises: when do I need architecture? Why is it important in one project, and why is it less important in the other project? So architecture acts as a skeleton of the system. So the metaphor of architecture as a skeleton is intended to describe how a skeleton provides the overall structure for an animal and influences what it can do. So most fast animals have 4 legs, but while the 2-legged ones are slower, they might be able to use tools more easily. Birds are good at flying and kangaroos are good at jumping, largely because of their skeletons. You cannot say, however, that one skeleton is better than another. have additional requirements that are not related to their function, referred to as non-functional or quality attribute requirements. And architecture basically influences these quality attributes. Now, accounting software that fails to account or animation software that fails to animate is not useful. But developers must pay attention to quality attribute requirements too. For example, accounting software that lets bad guys read secret accounts or animation software that runs too slowly is not particularly useful either. Another thing is, although a system's architecture is a separate choice from its functionality, a poor architecture choice can make functionality and quality attributes difficult to achieve. So here's an analogy. What your factory produces and where it is located are two distinct dimensions, and you can choose them independently. Putting a ship factory in the mountain is possible, but harder than putting it on the coast. With enough effort, you probably could build any system using any architecture, but developers will struggle when the architecture is unsuitable. All systems are constrained. Some must interoperate with older systems, some must use subcomponents from preferred vendors, and others must stay within memory or time budget. So, architecture is important because what it does, it defines components and their separation. And architecture partitions subsystems that can be created separately. Another thing that is important about the architecture is that it is a way to make buy versus build decision early in the project. In the meantime, mistakes made at the architectural design stages are difficult to recover from. And lastly, team organization and resource allocation that has to do with funding and getting money to pay developers is also being decided at the architectural stage here. Let us focus on a particular example throughout this section, that is the development of a home media player system. The home media player is like a normal computer and plays media, videos, audios, and pictures by connecting to television and optionally to stereo. One of the first things that one can do is identifying quality attributes and prioritizing them. Quality attributes are something that your customers value about your product. In some instances, the customer or requirements analysts are able to give you the prioritized list of quality attributes. In other cases, maybe you have seen how other media players worked and failed. So the goal would be to identify relevant quality attributes. So let's say we have identified these quality attributes. Let's assume we prioritize the quality attributes this way. Maybe most media players do their basic job playing back audio and video, but many fail to provide satisfactory solutions because their user interfaces are sluggish or differ in their ability to deliver smooth and reliable playback. And so you have decided that this is an important issue in the perception of your system. So such a ranking is trivially easy to write down and distribute throughout your team. It may simply inform everyone, or it may stimulate discussion about their priorities. A more explicit yet still lightweight technique of describing quality attributes is to write them down as quality attribute scenarios. A QA scenario can be described using a 6-part template. consisting of the source, stimulus, environment response, and response measure. This figure represents an example of a full quality attribute scenario for a commercial system. So QA scenarios work great for obviously measurable qualities like latency, and less well for qualities like maintainability and usability. You would like your system to be ideal in every quality attribute dimension, perfectly secure, perfectly usable, and unbelievably fast. But getting more of the quality attribute generally one quality attribute generally means getting less of another one, meaning that there is a trade-off between them. For instance, we care about portability, which is high on our priorities list. Portability usually means adding an extra software layer that provides a uniform interface to different hardware or software platforms. But unfortunately, the new layer increases latency and sometimes hurts the audio fidelity. Since we prioritize playback smoothness, we can code directly to the platform-specific APIs, knowing that this will make portability more difficult. So clearly, there's a trade-off. Often, there are tweaks that can improve audio playback, especially frame rates, that are dependent on the video source or codec. So let's assume that most video playback was happening sufficiently well on the hardware we had chosen. What we can instead do is a system that would allow to plug new codecs or video sources, thus making the system more modifiable. So this again is the choice between the two quality attributes of the system. You can investigate the suitability of your architecture by introducing prioritization to your quality attribute scenarios. To do so, you require that each quality attribute scenario is rated both by stakeholders and developers. Both rate the quality attribute scenario on a high, medium, and low scale, with stakeholders rating its importance and developers rating how hard it will be to achieve. This yields a tuple, such as hard importance, medium difficulty, usually shortened to just HM. Some quality attribute scenarios will be easy, the ones rated HL, and others are likely to be deferred or watered down, the ones rated LH. But others, usually the ones rated HH, are both important and hard to achieve. So developers will need to pay considerable attention to them as the system is designed. Such quality attribute scenarios are known as architecture drivers, because developers will use them as test cases when creating and evaluating architecture options. For our media player we can deal with our two highest priority quality attributes that are technically challenging to achieve. So, for example, architecture driver number 1 might be when a user gives a command, such as pressing pause on the remote control, the system should comply with the command within 50 milliseconds. And the second one might be that our reference H264 AVC video from local disk should play smoothly on the reference hardware. So these are the two crucial quality attributes that we would like to achieve. With an established prioritization of quality attributes, one may proceed with making other design decisions. For instance, one of the design decisions might read as: to promote reliability, each top-level component will run in its own process to isolate faults, like services in an operating system. Or the media rendering/playback component communicates using shared memory with the media buffer to minimize latency, considering the high rate of data movement. Since commonly you as a team would spend considerable time discussing the alternatives to these design solutions, and also those are hard to infer from reading the source code, you might want to include these statements in the descriptions for the new developers. Quality attributes describe observable properties of a system, and quality attribute scenarios describe requirements for quality attributes. Architecture drivers are quality attribute scenarios that need increased attention during design. And trade-offs are the ways of balancing quality attributes to achieve a desired result. The canonical model structure presented here provides you with a standard way to organize and relate the facts you encounter and the models you build. The essence of the canonical model structure is simple. Its models range from abstract to concrete, and it uses views to drill down into the details of each model. There are three primary models: the domain model, the design model, and the code model, as seen in this figure. The canonical model structure has the most abstract model, the domain, at the top, and the most concrete, the code, at the bottom. The domain model describes enduring truth about the domain. If something is just true, then it probably goes in that model. So in general, the domain is not under your control. In contrast, the design is largely under your control. The system to be built appears here, and here you make a partial set of design commitments, commonly leaving undecided some low-level details about how the design will work, deferring them until the code model. The design model is composed of recursively nested boundary models and internals models. A boundary model and an internals model describe the same thing, like a component or a model, but the boundary model only mentions the publicly visible interface, while the internals model also describes its internal design. Finally, the code model is either the source code implementation of the system or a model that is equivalent. Implementation facts like the customer address is stored in a varchar 80 field. Go here. So for a bunch of these videos that are going to follow, we are going to be using a lot of UML, which is a unified modeling language that is a general purpose developmental modeling language intended to provide a standard way to visualize the design of a system. For the sake of this video, we're not going to include much information on UML. However, there are plenty of resources available online that you may want to check out, like this series of introductory videos from Lucidchart, and I'm linking to those in the description. They obviously also provide the implementation of UML diagramming tools that you also might want to check out. So when we're starting to create a domain model, what we do is we create an information model that can be drawn graphically, as seen on this figure. So the graphical type of models have a benefit, meaning that the relationship between the types are explicitly expressed as associations. So this represents an information model of an employment website. In this diagram, a person is associated with many contacts, the set of which is called a network, and the contact exists between two people. So in this case, we're using UML class diagram syntax with UML classes representing types. Another way of putting this model would be to create a textual model, which is just a list of types and their definitions, as seen here below. So let's get to the design model that is describing basically the design of the system. So the design model is a comprehensive model with every possible detail in it, and such models and architecture are sometimes called master models. So you can of course think of a master model for domain or code. So in practice, what people typically use to describe their software architecture are views. A view is the projection of a model that reveals the details. We will use views to selectively narrow our focus of the comprehensive design model. In what follows, we're going to examine a variety of example views on the job advertisement system, specifically the ones described here. UML use case diagram provides a compact graphical overview of the functionality of the system and the actors and systems that interact with it. This figure shows a job advertisement system, several use cases, and member, non-member, and timer actors that use the system. In this example, the timer actor is special and indicates that some use cases run at particular times, each day as system internal jobs. The use cases are high-level functional descriptions of the system, like inviting a contact or accepting that invitation. Use case diagrams show what the system can do, but they do not impose any constraints or give only a little detail. To add details, functionality scenarios are commonly used to elaborate on what's going on. When, for example, the user clicks invite contact, the system is going to send an email to that contact and so on. The use case diagram allows to make some commitments, but keep other design options open. The system context diagram, as seen in this figure, is similar to the use case diagram in that it provides an overview of the system and the actors it interacts with. The biggest difference is that functionality is much more visible in the use case, while the system context diagram more clearly shows the connectors, which represent channels of communication to external systems. Because of this increase in precision, the context diagram encourages a more literal depiction of interactions. For example, here the interaction is intermediated by a web server and a web browser and an email client. So let's talk in somewhat greater detail about what components and connectors are. So each of the boxes in the system context diagram is a component instance or an instantiated component type. For the sake of clarity, it is useful to differentiate between instances and types for components, as those follow the same instance relationship, just as classes and objects do. In object-oriented programming languages today, you define classes in the language and see objects at runtime. Components are the principal computational elements and data stores that execute in the system. Components may only communicate either directly or indirectly using ports and connectors. And when you're drawing component diagrams, you should always show all of its ports and connectors. For the sake of this video, we're going to use the terms ports and connectors interchangeably. Connectors are pathways of runtime interaction between one or two or more components. Let's talk a bit in a bit more detail about the notion of connectors. Connectors enable components to communicate, but this should not be interpreted as a less important job. They can also do real work, and often that work is the communication that may happen. Connectors can convert, transform, or translate data types between components. They can adapt protocols and mediate between a collection of components. They can broadcast events, possibly cleaning up duplicate events or prioritizing important ones. Significantly, they can do the real work that enables quality attributes such as encryption or compression or synchronization. The concept of a connector is quite general and encompasses the common ways to communicate, including procedure calls in events, more complex mechanisms like pipes or batch transfers. It also covers indirect means of communication such as interrupts and shared memory. Some example implementations of connectors include remote procedure calls and enterprise service buses. Now, bearing that in mind, let's get back to our job advertisement system and look at a component assembly diagram. A component assembly diagram shows a specific configuration of the component instances. You have previously seen one special case of a component assembly, the system context diagram. The component assembly shows bindings between the external ports in the system and the internal ports inside the system, on the contacts, advertisements, and emails. A binding between an internal port and an external port means that any interactions with the internal port are handled by the internal port. It is not a connector and no work is being done there, but it's there for just for clarity. The last type of diagrams that is important to us in this video is the deployment diagram. As the system is being deployed onto hardware, the hardware and its configuration will impact how the system performs. This figure shows the component instances for the system being deployed both at a primary and backup data centers, which are examples of environmental elements, or sometimes simply called nodes. The figure also shows that the user's PC is connected to the data center by the internet, and then the primary data center is connected to the backup via an intranet. The diagram also shows how running component instances are allocated. Hardware, for example, that the user PC hardware is running an instance of the web browser. So canonical models from abstract to concrete, from the domain through the design all the way to code model. It typically uses UML notation, so I encourage you to get acquainted with that. The domain models are typically information models of enduring truth about the domain. The design models describe the system that has to be built. It is typically represented in many views, such as use case, system context, or deployment. We're commonly reasoning with components and connectors to more systematically represent our knowledge about the system design.